Hello, I wanted to do a quick little video here showing you how to deal with finding components of vectors. We have a vector here that's already drawn for us, the vector f, and we can see that this vector doesn't point just in the x-hat direction or just in the y-hat direction, but points in both directions. So it points up and it also points to the right. A lot of times we're going to have reasons to need to be able to find the components of the vectors in the x and the y direction. So I wanted to show you a way that we might be able to do that. So first of all, when I have my vector in a force diagram, this one is just by itself, but if I do, I'm going to want to draw out the x and y components of that vector. So I'm going to draw the x component of this vector, looked sort of like that. So you can see it points to the right just about as far as this vector points to the right. And then the y component of the vector would be up like that. And you can see that that points as far up as the vector f does. So I'm going to label these vectors. This will be f sub x, and I'm just not putting the vector notation above it, the arrow, because really I'm just interested in the magnitude of it. And this will be f sub y. So f sub x, however long it is the component of the vector f in the x direction. Now that just means that's how much the vector f points to the right. Likewise, f sub y is the component of the vector f in the y direction. It's how much that vector points up. So the way we find those is we use a little bit of trigonometry. So I'm going to construct another triangle here that's going to look like that triangle. So it's a right triangle because it has a right angle. And if I then label the sides of this triangle, we know that the long side is the hypotenuse. So I'll put an H there for the hypotenuse. This, of course, is the right angle. This is the angle theta, whatever it is. So it's very much like the triangle we have in our force diagram, where the hypotenuse is the force, which is always going to be the case. Now, f sub y here is opposite the angle. It's the one side of the triangle that is not involved with the angle theta. So I'm going to call that O for opposite. And this side of the triangle is adjacent to the angle. And so this, of course, is my angle theta. Now, for mathematics, we know that the ratios of these sides of the triangles are important, and that the ratio, like for example the opposite side divided by the hypotenuse, is going to be the same ratio for any triangle that has the angle theta in it. And it's important enough and used often enough to give it a special name, and this is called the sine of theta. Now the sine of theta is defined to be the opposite side of the triangle divided by the hypotenuse. Likewise, the adjacent side of the triangle divided by the hypotenuse is called the cosine of the angle. So cosine theta is equal to the adjacent side divided by the hypotenuse. Now these functions, sine of theta, cosine of theta, you can find the values for any given angle in your calculator simply by typing in, sine of theta. Depending on how the calculator is used, you might put the angle in first and then hit the sine button, or maybe you put the sine button in first and then enter the angle. It doesn't matter, you just need to know that for your own calculator. But the important thing is that that number is in your calculator, it's easily found. So if I wanted to solve, like for example, for f sub y, which is analogous to the opposite side of this triangle, I'd multiply both sides of this equation by h. And I would get h sine theta is equal to the opposite side. So if I knew what h was, and if I knew what the angle theta was, I could find the opposite side by taking the magnitude of the hypotenuse and multiplying it by the sine of the angle. That would be the opposite side. Likewise, h cosine theta is going to be equal to the adjacent side. And so these expressions are formulas for finding the opposite and the adjacent side of any triangle when I know the hypotenuse and the angle theta. So that's important to us because in a force diagram, the force is the hypotenuse of the triangle. So if I know the force and the angle it makes, I can find its components in the x and the y direction. So as an example, let's suppose that the force here, let's keep it something simple. Let's say the magnitude of that force is 100 newtons. Now notice that that is the magnitude. I just express it as a positive number regardless of which way it points, since really all I want to know is the length of that vector, which is 100 newtons. And let's say the angle theta is equal to 30 degrees. Remember to have your calculator set in degrees and not radians. So, by using this analogy, we see that f sub y would be the opposite side of the triangle, and so I could write the expression f sub y is equal to f sine theta. Sine because it's the opposite side. Sine goes with the opposite side of the triangle. Now, there's no arrow above the f because it's just the magnitude. So f sub y would equal the magnitude of f, which is 100 newtons. And if you look in your calculator and check for the sine of 30 degrees, you'll see that the sine of 30 degrees is 0.5. And this means that the y component of the vector f is 100 newtons times 0.5, which is 50 newtons. And so 50 newtons is the vertical component of the vector f, and it's positive because it points up. If the vector f had pointed down this way, for example, then the y component would be negative. We can do the same thing to find f sub x. Now, f sub x is the adjacent side of the triangle, so I'm going to use the cosine function. So that's going to be the magnitude of the vector f times the cosine of 30 degrees. Once again, f is 100 newtons, and the cosine of 30 degrees. Well, if you look this up in your calculator, it's about 0.8660. It's actually the square root of 3 over 2. Now, so that f sub x now is equal to 100 times 0.8660, which is about 86.6 newtons. And so we have the x component of the vector. Notice that if you add 86.6 and 50 together, you do not get 100 newtons. And the reason for that is we're talking about vector components, and they add together like vectors. If you were to add them together the way vectors add, I think you would find that it works out. How would you add them together like vectors? Well, you would use the Pythagorean theorem, and I'm going to leave that to you as an exercise, but I'll set it up down here. Verify for yourself that this is more or less a true statement. 100 squared, which 100 is the length of the hypotenuse, is equal to, if you remember the old Pythagorean theorem is like a squared plus b squared is equal to c squared. So 100 squared would equal 86.6 squared plus 50 squared. So go ahead and put that into your calculator, and I think you'll find that 86.6 squared plus 50 squared does in fact equal 100 newtons. So they don't add together the way regular numbers do. They add together the way that vectors do. I hope that helps.